and get things started. So, a couple things before we go ahead and get started. So I just wanted to do a bit of a quick introduction on who I am. So my name is Kitong Liu. You guys can call me Mr. Liu, call me Teacher Liu, call me whatever you want. I graduated from the University of Texas at Austin with a math degree. So that's really just a little bit about me. I currently work in insurance pricing, so I do a lot of math there. But yeah, so for this class, this is going to be our pre-algebra class from the start, and we're going to learn a decent amount about just like we're going to start from the beginning. We're going to do a lot of review-ish kind of topics at the start. And then from there, we're going to move on into maybe some more new topics towards the middle and the end. But right, so with that being said, I wanted to maybe say something about like a bit of the structure and the way that I want to do things. I am okay with leaving cameras off. I think it's just I think sometimes it can be really distracting, especially when I'm doing things on an iPad or like and I have things for you guys that I want you to see. That's what I want you to be looking at. So but yeah, and whenever I go through a lot of the questions, I'm going to try to go through and try to have everyone answer questions. With that being said, if you would like to unmute and just go ahead and answer directly, that's good with me. That's the fastest way. That's the easiest way. If you're a little bit shy or if you don't have a mic, feel free to go ahead and just answer with the chat box. If you're going to answer with the chat box, I would like you to like just type something to let me know that you're there first, so that I'm not just waiting and maybe you were off at the restroom or something. But yeah, so with that being said, I'm always looking at the chat. I'm always looking at the participant list. So if you have a question, feel free to raise your hand or just drop it directly in the chat. I'll be looking at both of those. If you have, and then if you want to unmute and directly ask me, feel free to do that as well. You don't need to wait for me to finish what I'm saying. You can feel free to. If it's a question that you really need answered, feel free to go ahead and interrupt me. I'll just start off where we left off if that happens. Um, as for those of you with Chinese names, I'm sorry, I can't read some of the characters. I'll try my best, but please forgive me. And lastly, what we're going to start with here is we're going to start with a couple of the basic arithmetic stuff. So starting off with this, I did want to take just a little bit of time to take a look at exactly what we're going to be looking over. So we're going to start by looking at arithmetic, then we're going to move into exponents, number theory, fractions, equations, and inequalities, moving on into decimals, ratios, percents, square roots, and then we're going to talk a little bit about geometry through angles, perimeter and area, and right triangles and quadrilaterals. And after that, we're going to finish up with data, counting, and some just putting it all together with problem solving. So with that being said, if this material looks easy, please look into maybe going into the Algebra 1 level course, into the Introduction to Algebra course. If this material is above your level, then maybe we could look into maybe moving down to another class. But with that being said, that's just a general idea of the material that we're going to be looking at. Just the table of contents here. We should take about two lessons for each chapter, maybe a little bit more than that for some of them if they're a little bit more important. But with that being said, let's go ahead and get started on chapter number 1. So chapter number 1, we talk about arithmetic. And the importance of this is really just, well, we've talked about, you all are very familiar with arithmetic at this point. It's something that you definitely have been learning ever since elementary school, right? Like the first few chapters were addition, multiplication, subtraction, division, right? Like those are things that you've learned in elementary school from first all the way up to 4th grade or something like that. That's probably when you were introduced to all of that. With that being said, though, right around pre-algebra, there's a bit of a change in the way we want to look at things. But because the way that this works is in algebra, we kind of rethink a lot of the ways that we take care of mathematics. So with that being said, we just really want to rethink a lot of the ways that you've been thinking about these addition, subtraction, or whatever. We just really want to think about these in a little bit of a different way. So even though it may be a bit of a repeat, it may be a little bit like we're reinventing the wheel. It might be like we're overcomplicating things a bit. But you might see that just because we did things this way, it might make more sense in the future. All right. With that being said, let's go ahead and get things started off. So Chapter 1 starts us off with talking about addition, but we're not learning about addition for the first time. Rather, we're talking about the properties of addition. So for the first question here, we are shown two figures. We want to explain why 2 plus 3 is equal to 3 plus 2. If the left side of this, or this drawing right here, is 2 plus 3, because the first row has 2 blocks and the second row has 3 blocks, then Anna, what does the right side represent?
It represents 3 plus 2 because the first row has 3 blocks and the second has 2 blocks.
That's exactly it. So with that being said, this shows us that for both the left and the right side, we have exactly 5 blocks, right? So it's exactly the same on both the left and the right side. This property is one that's really important in mathematics. This one is what we call the commutative property, C-O-M-M-U-T-A-T-I-V-E, commutative property. This is called the commutative property of addition. What this means is we can add the first number and the second number together, right? In this case, the 2 and the 3. We can add these two numbers in whatever order we want. It could be 2 plus 3, it could be 3 plus 2, right? Now, it doesn't matter what numbers we use here. It could be 3, could be 2, could be any other number as well, right? So if we want to express this with variables, is everyone here familiar with the concept of variables? If anyone's not familiar with them, please say so now, and I'll give an explanation as to what they are. Otherwise, I won't.
I don't know what they are.
Okay, so a variable is a placeholder. It's like we have a blank for something, but we say that this has to be a number, for example. That placeholder is usually a letter. And the most common letters that you'll see are usually going to be X, Y, and Z, right? A letter X or Y, right? So if we use, for example, X, and I say, and Melody, if I say 3X equals 15, if I told you that X has to be a number, what number would you say X has to be equal to here?
5.
5, that's right. So what's going on here is basically we're just saying we know it has to be a number. We just don't know exactly what number it is. So does that make sense? Kind of like what that X or Y, like what that kind of represents here?
Yes.
Okay, so basically now what I'm saying is that the commutative property states that if we have two such numbers that we don't know numbers of, if we say that X plus Y is equal to something, well, we know that X plus Y has to be equal to Y plus X. Between these two uses of X and Y, they have to be the same numbers. For example, in this case right here, X would be 2 and Y would be 3, right? It just lines up that way. And that's kind of what we're saying here, is we're just saying that it doesn't matter what order we add these two numbers in, as long as we add the two numbers together, it's always going to be the same thing. So let's move on to problem 1.2. 1.2 says that in this case, we have 2 plus 3, and then we add 4, and this is equal to 2 plus 3 plus 4. So if the left side here, 2 plus 3 is the first thing we do, so we're adding together the white boxes, and then we add the gray ones, the 4 gray ones. If that's what's going on the left side, then this is Sul, right? I'm not sure what the other two characters in your name are. Sorry. The number is 9350.
Can you repeat the question again?
Yeah, but first things, would you mind letting me know what's your name?
Su Zefei.
Su Zefei. Okay, yeah, I had guessed it was those, but I wasn't sure what inflection it was. All right, so the left side here, right? We see 2 plus 3 first. So we're adding together the white boxes first, and then we add on the 4 gray ones. So Su Zefei, what's going on the right side? What's going on here with this diagram here?
It's basically the same thing, except for they put the parentheses on 3 plus 4.
So what are we adding together to first?
3 plus 4.
Which would be the gray or the white boxes?
The gray.
Yeah, so Lillian jumped in here, but right, so these are going to be the gray boxes first, right? So what's going on the right side is instead of doing the white boxes first, we're now doing the gray boxes first. So that's exactly what's going on here. And we can see that if we do this, both sides is equal to 9. So we still are having the same thing go on here, right? So both sides are equal. And this is what we like to call the associative property. Right? This is important because combined between this property and the first one, we actually basically let us say that if we have a bunch of numbers, we can add them together in any order we want. As long as they're all being added, it doesn't matter how they're written. It doesn't matter in what order they're written. We can add any of them in any order that we want to. So that's the whole idea between these two right here. So the associative property, and then if we put some variables up to it, I think my app is frozen, but okay, actually, yeah, we're good now. But if we put some variables up to it, we get to see that we have a plus, it's frozen again. Okay, there we go. We get to say that a plus b plus c with parentheses here is equal to a plus b plus c with parentheses there. So that's what's going on here. All right. Let's move on into the next question. All right. So question 1.3. For this question here, we want to explain, first off, why these two are the same. So I'll take care of this part, but Allison, I'm going to want you to help me out with part B in just a moment, all right? So for part A here, what's going on is in these two equations, they look very similar, except the numbers are just in a little bit of a different order. But what we see is if we go ahead and swap the order of the 28 and the 219, we'll get 472 plus 28 plus 219, right? Now, what we did here was the commutative property. We swapped the order that the 28 and the 219 were written in. And then after this, we grouped the 472 with the 28 instead. And that puts us to at what we have on the right side. Now, with that being said, Allison, can you help me out with part B?
You mean like complete it?
Yeah, just go ahead and do this sum right here.
Okay.
So just talk it out through me and I'll write down anything that you want me to write down, all right? So no need for any pencil or paper or anything like that. Just talk it out.
219 plus 28.
So you want to do this part first?
Yeah.
So that's going to give you something a little bit tricky, right? Like 218 plus 28, you're going to need to carry that sum isn't really that easy, right? Now, what's the whole purpose behind this top part? What do you think we could do instead, maybe?
472 plus 28.
Yeah, so the goal here is basically saying, because all we're doing is adding together these three numbers, we can actually add them in any order that we want. So the order in which we're going to go ahead and add them in is actually the 478 and the 28 first. And then we're going to add the 219. But the reason why we want to do that is because 472 plus 28 is actually really easy, right? It's actually really nice because that's directly equal to 500. Now we have 500 plus 219, which is equal to what, Allison?
719.
And that's your answer here. So that makes things a little bit easier, right? So what's going on here is we're basically saying we can actually add together these numbers in any order we want. So we want to make things a little bit easier. Now, let's see this stepped up a notch. So Monica, can you help me out with problem 1.4 here?
Sure.
Mhm.
So you could first you could do 2 plus 12, which equals
Oh, so you're doing these first?
yes.
Okay, so I want you to think it back, right? If we do 2 plus 12 plus 22 plus 32, that's gonna give you an okay answer, right? But on this side, you're gonna need to carry a lot, right? So how can we maybe make this easier? Is there any way that would make this easier?
We could do 2 plus 8 and do the same for the rest of the 4 numbers.
Okay, so if we do that, if we do 2 plus 8 and 12 plus 18 and 22 plus 28 and 32 and 38. So what does 2 plus 8 give us?
10.
Mhm.
And the second one give us 30.
Okay,
With 50.
good.
Then
And
70.
okay, and at this point, we can go ahead and do these two first and these two together. 30 plus 70 gives us 100. 50 plus 10 gives us 60. So our total is going to be 160. But right, so this right here does give us our answer. And thank you, Monica. That does show us that we could have made things a little bit easier. Like it should be pretty easy to see that if we went ahead and we added together these numbers first and then these and then added together, that would have been a lot harder than what we did, right? But there's actually an even easier way than what we just did. In fact, if we combine 2 and 38, 12 and 28, 22 and 18, and 32 and 8, we'll find that all 4 of these sums is actually equal to 40 each, for a total of 160 as well. So this would have also been, this would have been even better. But what we did instead was a close second. All right, now with that being said, let's move on into the next set of questions. Problem 1.5 and 1.6. So 1.5 here is very similar to that question that we just did, 1.4. But I will say this question is a little challenging. So Catherine, let's see if you're up for the task. First things, Catherine, are you going to use the chat to answer?
Sorry, what?
Okay. All right, Catherine. So help me out here, right? So for this question here, we're looking for the sum of the numbers 1 through 20. So we're going to add all these numbers together, 1 plus 2 plus 3 plus 4, all the way down to plus 19 plus 20. Now, I told you that for this question, we're going to want to take a look at it kind of like how we did the previous question, where we grouped together the numbers such that we got easier numbers to work with, right? So what groupings do you think we would do here, Catherine? What groupings would you like to do? If you're not sure, we can throw it over to someone else.
Every 10 numbers.
Every 10 numbers? So
Or 5. Every 5 or 10.
Well, for the previous question, when we had that 2 plus 12 plus 22, right? We had grouped together 2 and 32 to make 40, right? So maybe there's something that we can do along those lines, Catherine? maybe. So what we see from here on what Julian had said was that we can actually group together the 1 and 20, right? And then after that, Melody, I'll go ahead and ask you. So after that, what do the rest of the groupings look like? Just give me a couple of them. Melody?
What?
So what do some of the other groupings look like? So Julian listed out the first one, 1 plus 20. That's definitely one way to do it. But what would the other groupings here look like in that case?
2 plus 19, 3 plus 18, 4 plus 17, 5 plus.
So
16.
yeah, and that's exactly what it looks like here. But what's the whole purpose behind that? Like, how does that give us the answer here?
All of them equal 21, and there's 10 groups, so you multiply 21 times 10.
Yep, and that's definitely one way to do this. And Catherine actually suggested, I don't think anyone else can see this because it's a direct message, but there's also another way to do this, which would have grouped together 1 with 19, 2 with 18, and all the numbers would be grouped up such that they all sum up to 20 instead. And then this 20 is on the end on its own, right? But then there's one key thing that you have to make sure that you remember if you do this way. You have to recognize that 9 groups with 11 and 10 is left alone. So you have to add 10 at the very end. If you do things this way, you'll have 1 through 9 groups of 20, which means a total of 9 groups of 20. And then you have the 20 alone here for 10. So 200 times 10 is 200, 20 times 10 is 200. But then you have the 10 remaining at the very end that you need to add back in. So your total is, once again, 210. So with that being said, this definitely has a lot of ways to do it. There's multiple correct ways to do this question. And getting 210 through any of them would get you to the right answer. And actually, this is a famous kind of question. This was actually originally from a lot of sources. This is actually originally a punishment for a mathematician. And the reason why it was a punishment was because he was annoying in class or something, but he was asked to sum up the numbers 1 through 100. But once he realized that if he could just go ahead and write down the numbers 1 through 100 this way, and then if he rewrote it again backwards, then added all of them up this way down here, each sum is the exact same number. How many of these does he have? Well, he has 100 numbers here, so he has 100 101s here. But what's the first thing he did? The first thing he did was he wrote it again. That's the same thing as doubling it. So 100 times 101 divided by 2 is his answer here. And what we can see is the sum of numbers from 1 to any n, to any number that we end at. So 1 plus 2 plus 3 plus 4, all the way down to plus n. This is simply just equal to n times n plus 1 divided by 2. Well, in this case, n equaled 20, right? So there's actually a formula for this kind of question here. All right. For our last question here, we simply just have proving why 2 plus 0 is simply just equal to 2. This idea here is that if you don't add anything to the number, that number just stays the exact same. So that's why this number doesn't change, right? So this idea is what we like to call the zero property of addition, and it's going to be very important when we talk about some negative numbers in just a moment. But all right, with that being said, let's move on into the next section. The next section after this is multiplication. With multiplication is just repeated addition. So with this in mind, we actually get a couple of ideas here as well. So let's take a look. So on the left side here, we have 2 times 3, right? 2 rows of 3 items each. So that's why that is 2 times 3. Now, Emily, can you explain what the right side is then?
The top is 2 and the sides are 3, so 2 times 3.
So we're actually looking at what we're trying to describe this as 3 times 2. So could you maybe change the way that you describe that just a little bit?
Okay. So the sides would be 3 and the top would be 2.
Yeah, so we have 3 rows of 2 items in each row, right? So that brings us up to the exact same answer of 6 on both sides. Now, Emily, one more question for you. I promise, just one more. With that being said, does this look like another property from addition that we had?
The commutative property.
Yeah, so this right here, we call this the commutative property of multiplication. So addition and multiplication both share commutative properties. It doesn't matter what order we write those numbers in, as long as it's the same 2 numbers being multiplied, it will always end up being the same answer. So in this case, if we're looking at x times y, this is just equal to y times x as well. All right, moving on. And as always, if you have any questions, feel free to ask me in the chat. If you're shy and don't want everyone else to see your question, send me a direct message. I'll read it. I'll need to read it out, but I won't. I'll try not to forget to just go ahead and not say who asked. But as for as for those who like to go ahead and unmute, like you can feel free and just unmute and ask me a question as always. But if there's no questions, we'll just keep on going here. Problem 1.8. By counting these dots in 2 different ways, we want to explain why 2 times 3 then times 4 is equal to 2 times 3 times 4. So if we look at this question on the left side, we have 2 times 3 first, so that would be 2 rows of 3 squares. So we count the number of squares there are in total, and then we count the number of dots in all the squares added together. That's what that is going on here. With that being said, Evan Liu, what's going on the right side here?
Oh, what? I didn't hear.
Yeah, so on the left side, we have 2 times 3, then times 4, right? So that the way that we can explain that is 2 rows of 3 squares in each row. So we count the number of squares first, and then we count the number of dots in each square, right? So what's going on the right side? Like, how is that 3 times 4 any different from this?
It's
If you're not sure,
all squares with 2 dots in each.
are there any squares with 2 dots though? I don't really think so.
What?
Like
What was the
what's yeah, so the way that we can look at this left side, right? The left side is 2 times 3 then times 4, right? So 2 is the number of rows, 3 is the number of squares in each row, right? And then so we count the number of squares first, and then we count how many dots are in each square. On the right side, we have 3 times 4 first. So 3 is how many squares there are in each row, right?
Yeah,
Then what's the 4 here?
the number of rows.
Is it though? Is it the number of dots in each square?
The number of rows.
I count 2 rows here, not 4. You see what I'm saying here? So the 3 times 4 would be the number of dots in each row. Would that look good to you? Because the 3 is how many squares there are in a row, and the 4 is dots in each square. So 3 times 4 is how many dots there are in a row. Does that make sense?
Oh, okay.
Yeah, and then after that, we multiply that by 2 to get the number of dots in total. Does that sound good?
Oh,
Yeah. So what's going on here is the left side is we're counting the number of squares that are first, then multiplying by the number of dots per square, while on the right side, we're saying how many dots there are per row, and then multiplying by the number of rows. So this here looks a lot like the associative property from addition. And likewise, we actually also call this the associative property of multiplication. So this is once again the associative property. So between both the associative property and the commutative property, these are shared between both addition and multiplication. It's the exact same idea. So for multiplication, this allows us to say, if we have numbers multiplied together, we can multiply them in any order we want to. It will always be the same. For example, A times B times C is equal to A times B times C, right? So we can do this in any order we want. We can go ahead and take a look on question 1.9. So Joshua, question 1.9 here says that we want to multiply 25 by 125 by 4 times 6 times 8. Now, Joshua, for this question here, we could do that in this order, but 25 times 125 is a bit hard. So what order would you recommend doing here instead?
First, I would recommend multiplying 125 by 8. That makes 1,000. Then 4 by 6, 24.
So 4 by 6 is 24. What about 24 times 25?
24 times 25. Actually, 24 times 1,000. Then 25 times that.
So 24 times 1,000. So 24,000 times 25, like this.
Yes.
So would things be easier if you did 4 times 25 first instead? What is that?
Oh, oops. Forgot.
You're good, you're good, you're good. No worries, right? But so the key importance here is to recognize that if we switch the order of these numbers a little bit, if we go ahead and multiply the 8 by 125, like you said, that makes 1,000. 1,000 is much easier to work with than 125, right? So if we do that, we get 1,000 here, we get 100 here. 1,000 times 100 is just 100,000 times 6 is equal to 600,000. So that brings us to a pretty easy answer there. All right. And lastly, with problem 1.10, we're just explaining why 2 times 1 is equal to 2. This idea here is we have, well, one item per row for 2 rows. That's still equal to 2, right? So 1 times anything is equal to itself. Same idea as 0 plus anything is equal to itself. So these are a little bit different between between multiplication and addition, right? One of them it's 1, one of them it's 0, right? Now, with that being said, let's look at the next set of problems here. All right. Problem 1.11. For this question here, we just want to look at how these two numbers are a little bit different. So Julian, part A here asks us what is 5 plus 6 times 7. So what do we need to do first here, Julian?
Add the 5 and 6.
Right, and the reason why we need to do that first is because 5 plus 6 is in parentheses, so we have to do that first. So that becomes 11 times 7, which is equal to 77. And what about the second part here, Julian?
You do 6 times 7 first, right?
Right, because again, parentheses dictates the order, right? That would be 42 plus 5 is 47, right? But what if there weren't any parentheses at all? If there weren't any parentheses at all, we would follow what we call the order of operations. Now, normally the order of operations is PEMDAS, or P-E-M-D-A-S, where P stands for parentheses, E stands for exponents, N stands for multiplication, division, addition, and subtraction. Please let me know if you can't read this, but hopefully having read it all out, it's pretty understandable. But the key thing here is we go from top down with a couple of exceptions. Multiplication and division are actually done at the same time, as well as addition and subtraction. And we're going to address why this is the case in actually next week's class, why subtraction is the same time as addition and why division is the same time as multiplication. But with this being said here, parentheses and exponents go first, but you can clearly see that multiplication happens before addition. So that's why if there weren't any parentheses here, 5 plus 6 times 7, we would still do 6 times 7 first. All right, let's take a look at problem 1.12. In this question here, we want to explain why 2 times 3 plus 4 is the same thing as 2 times 3 plus 2 times 4. So as always, I'll explain what the left side is. The left side is we do 3 plus 4 first. So we're counting together how many blocks there are in total in the row. 3 gray, 4 white equals 7 in total, times 2 is 14. With that being said, Lillian, what is the right side here? Lillian, did you answer the question? I don't think I heard an answer for that. Maybe your mic isn't really working. I'm not sure.
The
Okay.
right side.
Yeah, I hear a weird white noise, but I heard her say the right side, but nothing else after that. So go for it. It's all right. It's all right. If you wouldn't mind, just go ahead and drop your answer in the chat, I guess. But what's going on here on the right side here? So the 2 times 3, that's going to be representative of. Oh.
Yeah. 2 times 3 is 6.
Mm-hmm.
And 2 times 4 is 8.
Right, but what do the 2 times 3 and the 2 times 4 represent here?
6 plus 8.
Right. But I'm asking like in terms of this diagram here, right?
Oh, the 2 times 3 is shaded and and the 2 times 4 is not.
Yeah, so what's going on here on the right side is the 2 times 3 represents the shaded squares or the gray squares, right? The 6 gray squares on the left side of this diagram, while the 2 times 4 represents the 8 unshaded, the white boxes on the right. So what we do here is we're just saying that in this case, we're counting together the gray squares first and then the whites and then adding together instead of counting how many there are in each row. But you can see that with this way, it's still equal to 14, right? So Lillian, do you actually know what this property is called? Maybe Allison knows?
Something like associative.
Yeah, I was gonna say that associative property.
Associative? Oh, sorry. I thought you just forgot to unmute. I thought you just forgot to mute. The associative property was actually what we talked about earlier, right? It was that A times B times C where you do it in different orders, right? So I don't see any order changing here. And actually, this is a little bit different, right? Because that was all multiplication the entire way through, while and the same thing for addition, right? The addition associative property was the entire way through, right? It's all addition the entire way through. But here we have a mix and match between addition and multiplication. So this is actually what we call the distributive property. Distributive property. So what's going on here is we're actually kind of using both addition and multiplication here. So things are being combined here, right? If you have only addition or only multiplication, you have associative and commutative. But in this case, we have both put together. We have multiplication here and addition here, right? Now, we actually, the commutative property would allow us to say that we can put 3 plus 4 before the 2, right? We could do 3 plus 4 times 2 instead. This would be commutative of multiplication. We could also do 3 plus 4. We could also do 4 plus 3 instead. That would be commutative of addition. But this splitting up of the 3 and the 4 is what we call the distributive property. And you can see that now we have 2 2's, not just 1. But if we want to represent this as variables, we can see that this looks like a times b plus c is equal to ab plus ac. This is the typical way that you'll see this. You'll see this go from the left to the right. But what's actually pretty challenging for a lot of people is to see that it also goes the other direction. So, Melody, question 1.13. How would you like to do this question here?
What does that dot between 51 and 9 mean?
Yeah, so this just means multiplication. We can write multiplication as 3 different ways. We can do something like 3 times 4. We can do 3.4. We can also do 3 times 4 like this. Those all represent multiplication. So with that being said, what does this look like here?
51 times 9 and 51 times 31, and then add those two together.
Okay, so with the new distributive property that we just talked about, is there any way to make this easier?
I don't know.
You're not sure? All right, we can throw it over to someone else then. How about Michael? Can you help me out here?
Can you repeat that?
Yeah, so is there any way to make this easier and so that we don't need to multiply 51 by 9 and 51 by 31 here?
I'm not sure.
You're not sure? Well, does this look like the left side or the right side here?
What?
Does this right here, does this equation look like the left side or the right side of this one?
It looks like the right side.
It looks like the right side. Well, could you tell me what value each of the letters has then?
A is 51 and B is 9.
And
Oh,
then
wait,
C
and
is?
C is 31.
Right, so then if we plug in these numbers into the left side instead, that would give us 51 times 9 plus 31. Does that look good to you?
Yes.
So if we do this, then what is this going to be equal to? What would we do first?
Multiply 51 and 9.
That's if we
Oh,
did
wait.
this. So what would we do?
9 plus 31, right?
Which is?
40.
Right, so then this becomes 51 times 40, which is a lot easier than what we had going on here, right? So does that look good to you, Michael?
Yes.
And then for this, what we could actually do is we could say that 51 is actually equal to 50 plus 1 times 40, which splits apart to equal 40 plus 2,000, because 40 times 1 is just 40, and 40 times 50 is equal to 2,000. So your answer is 2040. All right, one final question here. Question 1.14. Question 1.14 here, we're actually expanding this a little bit. We're trying to see, does this work with more numbers? So Yvonne, I think that's Wang Yifan, right? Wang Yifan, I think. But Yvonne, so for question 1.14 here, is there any way to make this easier?
If you move the numbers around.
Sorry, can you speak up a little bit? I didn't quite hear that.
The numbers around.
Yeah, move the numbers around. So how can we combine them maybe here?
You could first add the numbers.
Which
Maybe
numbers would you be adding?
13 and 51.
13 and 51. So if we wanted to add those numbers together, 13 and 51, we'd have to have them being multiplied by the same number, which would be 17 and 13. But that's not quite the case, right? So instead, what numbers would we be adding?
I'm not sure.
You're not sure?
Yeah.
All right. Well, maybe we can turn to Anna for some help here. Anna?
We add 17, 51, and 32
And why is that the case?
because they're all being multiplied by 13.
So Yvonne, does it look good to you as to why we add these numbers together instead? Because they're all multiplied by 13.
Yeah.
Yes, like you can see from here, it's these two numbers we add together to 3 and a 4 because they're both multiplied by 2. And the same way here, these are all multiplied by 13, so we add up these numbers here. 17 plus 32, that's equal to 49. 49 plus 51, that's equal to 100. Multiply that by 13, and you get your final answer of 1,300. And with that being said, that's the end of this section as well. So we'll move on into our third section for today, which is negation. Now, we're just going to take a quick look at this page. So we're not really going to go too much into detail on this one here. But the idea of negation is that there are numbers to the left of the number line, right? So we've all heard about negative numbers before, hopefully. You should have learned that sometime in elementary school. But the idea here is that there are numbers bigger than 0, and there are also numbers less than 0, right? So with that being said, if we move left of 0, the same distance as we would have moved to the right, we get to the same number, but now negative, right? And what we can actually do is if we add those numbers together, say for example, 2 and negative 2, we get back to 0, right? Because positive 2 is 2 moves to the right, negative 2 is 2 moves to the left. That puts you right back at 0, right? So if this is the case, then what we like to call the negation of a number is simply just the negative form of that number, right? Or the number that when added to itself is equal to 0. So our example here would have been that 2 plus negative 2, right? This equals 0. So this right here means that negative 2 is the negation of positive 2. But if that is the case, we actually know, one of the things that we learned was that we can actually do these in any order we want. So we can do this in the reverse order, or negative 2 plus 2 is equal to 0. So if the first line meant that negative 2 is the negation of positive 2, then what is the other one? I think your name is Wang Li Na, is that right?
Can you repeat that?
Yeah, so did I get your name right first?
Yes.
Okay. So the first line here is basically saying that negative 2 is the negation of positive 2 because 2 plus negative 2 is equal to 0. With that in mind, what is the second line saying here? So for the first line, we said negative 2 is the negation of positive 2. So if we repeat that here, what do we see?
Negative 2 plus 2 equals 0. So negative 2 is the
Negation?
negation of 2.
Yeah, so that's what we said for the first line. Negative 2 is the negation of positive 2. But the orders are swapped here. So what does that look like now?
Just flipped over.
So positive 2 is the negation of negative 2. Does that look good?
Mm-hmm.
So that's the big deal, right? So positive numbers are the negative form of negative numbers, right? So if we look at that, and if we look at, say, a couple of negations, right? The negation of 4 is negative 4. The negation of 3 is negative 3. The negation of 2 is -2. The negation of 1 is -1. The negation of 0, we can see that on the right side, we're adding 1 each time. So if we keep on doing this, we actually get 0. The negation of 0 is 0, right, Catherine, as you pointed out here. And if we keep going, the negation of -1 is +1. The negation of -2 is +2, right? So the negation of 0 is itself. There is no such thing as a -0. And the negation of negative numbers is once again positive. So that's the whole idea here. And if we use something similar for multiplication, we can see that let's say 7, right? So 7 times 4 is equal to 28. 7 times 3 is equal to 21. 7 times 2 is equal to 14. 7 times 1 is equal to 7. If we keep on going, we can see that we're subtracting 7 each time we go down here, right? So if we do that one more time, we get 7 times 0 is 0. And what this lets us know is that any number times 0 is equal to 0. Any number times 1 is equal to itself. And if we keep on going with the negative numbers, we'll see that a negative number times 7 is a negative number, especially -1. -1 times any number is just the negative form of itself. 7 times -2 is just equal to the negative form of 14, or the negative form of 7 times 2. With this idea in mind, this is actually something that we want to make use of, because right here, this fact allows us to say that -1 times any number x is just equal to -x, the negative form of that x. So if we use this idea for a couple other numbers, let's say, for example, -2 times 3, this is just equal to -1 times 2 times 3. And with the associative property, we can do 2 times 3 first, which would be -1 times 6. And then back here, -1 times 6 is just equal to -6. Any questions here? And likewise, if we do something similar with -2 times -3, we get that this is equal to -1 times 2 times -1 times 3. If we do the -1 multiplied first, we get that this is -1 times -1, right? Well, -1 times -1 is just the negative form of -1, and we said that this was just the positive form of itself instead. So a +1 times 2 times 3, which is equal to 6. And lastly, if we look at one final example, if we have -4 plus 5, this here, what we can do is this is equal to -1 times 4 plus 5, which is equal to -1 times 4 plus -1 times 5, because this we used the distributive property, and then we use that property of the negative signs once again, so this becomes -4 minus 5, or -4 plus -5, however you want to look at it. And with that, that's actually the conclusion of our third section for today. So today we talked about addition, multiplication, and negation. Next time we're going to talk about, we're going to finish up this chapter by talking about subtraction, reciprocals, and division. And from there, that will end chapter 1. And yeah, so that's going to be it for today. We're ending just a little bit early, but homework is going to be the review problems from from sections 1.2, 1.3, and 1.4, the 3 sections that we covered today. If you guys thought that this was a little bit easy, it is. It's a bit of a review from elementary level things. Like, hopefully these are all things that you have heard of in the past. Maybe it's been a little while since you've worked with it, so no worries about that. homework is going to come straight from the textbook. If you don't have the textbook already, it's the Art of Problem Solving Pre-Algebra book. If you don't have that, stay tuned on the WeChat group. We might be doing something about those, about the textbook. But the homework is just going to be on the end of each section. It's going to be on the end there. If you don't have Weixin, most likely your parents do. I think that was pretty much where we made this group. So, but if you don't have that, we can look to find. We can figure out something. But right. So, with that being said, oh right. So if this section was a little bit easy, this does pick up pretty quickly. So next, the next chapter is going to talk about exponents, and we're going to move on from there into more challenging things. So with that all said, if there's no questions here, you're all free to go. And if you have a question, feel free to speak up.
Bye.
All right, thanks. See ya. All right.
Where are you gonna send the homework again?
So I just said what the homework was. Like it's going to be sections 1.2 through 1.2 through 1.4.
Coop is so cool.
In the website?
I'm not. So I don't know if we have a website just yet. You can go ahead and there's going to be a. I think we're going to make a Padlet or something. If we do there, I'll post up homework there. But yeah,
Okay.
yeah, does that sound good?
Yeah, bye.
Okay. See ya. Yvonne, did you have any questions?